All right, so for section 4.4, we're going to talk about exponential and logarithmic equations. So first, we're going to start off with exponential equations. Remember that you're going to have the base to a power equals base to a power, and what's making these exponential equations is that there's a variable in the power. One of the things to keep in mind, or one of the things that we're going to talk about, is that if we have base to a power equals base to a power, if it is the same base, then we know that the powers have to be equal also. So if we can rewrite an equation into this form, then we can kind of just drop the bases. So let's look at a couple of examples. For our first example, we have 32 to the x equals 8. Now obviously these are not the same base, but we can rewrite 32 and 8 in base 2. So 32 is the same thing as 2 to the 5th power. So the 2 to the 5th is the same as 32. So this would be 32x equals, and then 8 is going to be the same as 2 to the 3rd power, or 2 cubed. Now using our exponent rules, we're going to multiply these exponents, so this 5 and this x. So we're going to have 2 to the 5x equals 2 cubed. And once we get here, we can basically just drop our bases. What we're doing, really, is we're taking log base 2 of both sides. But again, you can just think of it as dropping your bases. So log base 2, this is going to allow us to be left with just 5x equals 3. And then when we solve, we're just going to divide both sides by 5. And we're going to get x is 3/5. We can put this back into our equation to double check, or we can double check with our calculator by doing 32 to the 3/5 power. So 32 to the power of 3/5 should give us 8. And sure enough, it does. All right, for B, we have 8 to the x plus 3 equals 16 to the x minus 1. Again, we can rewrite these in base 2, that 8 and that 16. While those are currently the bases, we can rewrite those in base 2. So we're going to start off rewriting 8 as 2 cubed. So this is 8 to the x plus 3 equals this 16, that's the same as 2 to the 4th power to the x minus 1. Now again, we're going to do just like we did over here and multiply these powers, because this is a power to a power. The one thing to keep in mind that's a little bit tricky is this exponent is considered one thing, so think of it as having parentheses around it. So if you think of it as having parentheses around it, then you should do really well whenever we multiply through here. So we're going to have 2, and this is going to be to the, we're distributing, so 3x plus 9 power equals 2, and we're going to distribute here to the 4x minus 4 power. And again, once we have the same base, we're going to drop those bases. We're going to be left with 3x plus 9 equals 4x minus 4. And if we pull our x's over to the right, so we're going to subtract 3x from both sides. So we've got 9 equals x minus 4, and then just add 4 to both sides. And we're going to get that x equals 13. We can plug that in to double check. So we have 8 to the 13 plus 3, or 8 to the 16th power. So 8 to the power of 16, okay, it's going to give us this nice long number, times 10 to the 14th. And so we're hoping that when we do 16 to the power of, so 13 minus 1 will be 12. So 16 to the 12th power, that we're going to get the same thing. So 16 to the 12th power, and sure enough, we do. So we for sure have gotten the right value for our x. All right, and then C. So C, we have the same base. We're looking at this as in base E. The only tricky part is to rewrite this 1 over E as e to a power. So the first side, the left side, is already done. So e to the x plus 1 equals, and we know we want this in base E. Remember that if you have a power, or have a base that's on the bottom or went to the denominator of a fraction, then that means there was a negative exponent. So this is the same as e to the negative 1. So once we have e here for the base on both of these, we're going to have x plus 1 equals negative 1. And subtract 1 from both sides, and we get x equals negative 2. And again, we can double check that the exact same way by plugging in a negative 2 here. So e to the negative 2 plus 1, or e to the negative 1, equals 1 over e, which is the same as e to the negative 1. All right, so sometimes we're not going to have the same base on both sides. Or we're not going to be able to rewrite both sides with the same base. For example, on A, we have 19 to the x power equals 143. 143 is not a power of 19. So we can use logarithms, and we're going to choose to use natural logarithms, or ln, so that we can get the exponent down. So with this first one, we're going to start by taking the natural log of both sides. So we're going to have the natural log of 19 to the x equals natural log of 143. And the reason we're doing this is so that we can take this x and put it down in front. We're going to use our power rule. So the power rule is going to allow that to come in front. So we're going to have x times the natural log of 19 equals the natural log of 143. And then we're actually almost done. So to get x by itself, we just need to divide both sides by the natural log of 19. So we're going to end up with x equals the natural log of 143 over the natural log of 19. One of the big things I want to point out here is that we can't combine these. So we cannot combine this to just be the natural log of 143 over 19. It's the natural log of 143 divided by the natural log of 19. So my math lab is going to ask for the exact answer in terms of natural logarithms, and that would be this. And that is going to be approximately equal to, and they're going to ask for an approximation. So you're just going to put this in the calculator. So we're going to have the natural log of 143 divided by the natural log of 19. Let me get that 1 in there. So it's going to be about 1.685. All right, so for B, we're going to try the same thing because, again, 410 is not a power of 7. So we can't do 7 to any power to get 410. So since we cannot rewrite these in the same base, we're going to do the natural log of both sides. So we're going to have the natural log of 7 to the x plus 2 equals the natural log of 410. And the reason, again, that we're doing the natural log of both sides is so that we can take this exponent and put this exponent in front. So we're going to use our power rule. And again, this is a little bit of a tricky spot. So remember on the last page that whenever we had an exponent that was more than one part, so meaning more than just x, we had to think about it as having parentheses around it. We're going to do the same thing here. So whenever we pull that out front, we're going to have x plus 2 times the natural log of 7 equals the natural log of 410. So to get this x by itself, we can first divide by that natural log of 7. And that's going to give us that x plus 2 equals the natural log of 410 divided by the natural log of 7. And then we're just going to subtract 2 from both sides. So our final answer is going to end up being that x equals the natural log of 410 over the natural log of 7, all minus 2. And again, if your calculator, or sorry, if you're wanting a decimal equivalent, just use your calculator. So we're going to have the natural log of 410 divided by the natural log of 7, and go over, and all that is going to be minus 2, and that's going to give us about 1.092. So that's about equal to 1.092. And these little squiggly equal marks, that's just saying approximately. All right, for our problem in C, this has an extra step. So we need to get the base and the power by itself on one side before we can take the natural log and use our power rule. So the first thing we're going to do is add the 7. So we're going to add 7 to both sides. And then that's going to leave us with e to the 4x minus 5 equals 11,250. Now that we have the base and a power all by itself on one side, now we can take the natural log of both sides. And whenever we do that, again, the whole point is that we can take this exponent here and use our power rule and put that in front. So we're going to end up with this 4x minus 5 times, and this is technically times the natural log of e, equals the natural log of 11,250. But I want to remind you that the natural log of e, that's the same thing as 1. So the natural log of e is the same thing as 1. So this is the same as multiplying by 1, which means we don't need that. So we just have 4x minus 5 equals the natural log, oops, there we go, natural log of 11,250. And then we are going to add 5 to both sides. So we have 4x equals the natural log of 11,250 plus 5. I want to make a big note for you that this plus 5 is not, you cannot add that to the 11,250. This is the natural log of 11,250. So that plus 5 we cannot just put in there. All right, and then our last step is just going to be to divide by 4. And we're going to end up with x equals the natural log of 11,250 plus 5 all over 4. And again, if it wants an approximation, a decimal approximation, we're just going to put that whole thing in the calculator. So we're going to do the natural log of 11,250 plus 5 all divided by 4. And that's going to give us about 3.582. Okay, so let's talk about some more equations where we can use the definition of logarithm to solve. So essentially, if they're given to us in the form of a logarithm, we can, some of the time, convert that into the exponential form and then solve the ways that we've used on the last 2 pages. So for A, we would start off of log base 4 of 3x plus 2 equals 3. This base 4, so we're going to have 4 to the third power equals 3x plus 2. Well, once we have it as 4 to the third power equals 3x plus 2, we can just simplify that 4 cubed, or we can work it out, and that's going to be 64 equals 3x plus 2. And then we're going to go through and solve like we normally would. So we're going to subtract 2 from both sides. So we're going to get 62 equals 3x. And then divide both sides by 3. So we're going to get that x equals 62 thirds. So we can double check that. So we have log base 4. So we can use our little log button. Alright, so we're going to plug that into our calculator to double check. So we're going to use our log where we can put in the base. So log base 4 of 3. And then so 3x is going to be 3 times 62 over 3. Plus 2. And sure enough, we're going to get 3. So one of the things that we need to make sure of is that any value of x that we get, that whenever we plug it into the original problem, that we're not trying to take log of 0 or a negative number. Remember, for the domain, this of part, so this 3x plus 2, has to be greater than 0. So let's look at another example. So for b, log base 6 of x plus 3 plus log base 6 of x plus 4 equals 1. Now remember, if we use our product rule, whenever we see this plus and we have log base 6, so log base 6 for both of these, that's the same as multiplying. So we can combine this into one log statement. So one log expression, so we have log base 6, and we're going to have that x plus 3 times x plus 4 equals 1. The brackets are here to let you know that it's log base 6 of both of these things. Now, once we have it written as combined into one log statement on the left, then we can do 6 to the first power equals x plus 3 times x plus 4. So 6 to the first power equals x plus 3 times x plus 4. And to go through and solve, so we're going to have 6 equals, we're going to need to FOIL. So we're going to have x squared plus 4x plus 3x plus 12. So we have 6 equals x squared plus 7x plus 12. We're going to subtract 6 from both sides. So we get 0 equals x squared plus 7x plus 6. And whenever we factor, we're going to get x plus 6 and x plus 1. So now we set each of those factors to 0. We're going to end up getting that x is negative 6 and x is negative 1. Now again, we have to double check our answers. So whenever we come back up top, if we plug in that negative 6, we're going to be trying to take log base 6 of negative 6 plus 3. That's going to be log base 6 of a negative 3. We cannot take log of a negative, so we know right away that this x equals negative 6 is not going to work. So that one is not going to work. What about this x equals negative 1? If we plug the negative 1 in, we're going to have negative 1 plus 3, which will give us 2, which is greater than 0, and negative 1 plus 4, which is 3, again, which is going to be greater than 0. So we are going to be okay using the x equals negative 1. And remember, you can always put your number in and double check. So you could actually put this into your calculator. All right, for part C, we're going to use our quotient rule because we have log base 4 of x plus 2 minus log base 4 of x minus 1 equals 1. So again, with the quotient rule, we're thinking about division. So we're going to combine this into one log statement. So we're going to have log base 4 of x plus 2 divided by x minus 1 equals 1. Once you have one log statement, then we can go through and convert this over into its exponential form. So we're going to have 4 to the first power equals x plus 2 over x minus 1. So 4 to the first power equals x plus 2 divided by x minus 1. So x minus 1. And that's going to be the same thing as just 4 equals x plus 2 over x minus 1. So now, to get it so that we don't have x minus 1 on the bottom, we can multiply both sides by x minus 1. So we're going to end up with 4 times that x minus 1 equals, these are going to cancel, x plus 2. We'll then need to distribute, so we're going to have 4x minus 4 equals x plus 2. Subtract x from both sides. So we're going to have 3x minus 4 equals 2. And then add the 4. And we've got 3x equals 6. And then just divide both sides by 3. We're going to get x equals 2. And if we come back up and look at plugging in x equals 2, we're going to have 2 plus 2, which is 4. This will be positive. And then 2 minus 1, which is 1, which will also be positive. X equals 2 is going to work. All right, let's talk about the one-to-one property of logarithms. This is a similar idea to whenever we have the same base to a power equals the same base to a power, that we can drop the bases. Well, if we have one log statement on each side and it's the same base, then we can drop the log statements. So for A, we have 2 log x minus log 7 equals log of 112. We can combine this into one log statement, so into one logarithm. To do that, we're going to first use our power rule. So this 2 is going to come up to this x as x squared. So we're going to have log of x squared minus log of 7 equals log of 112. And now we can use our quotient rule to combine these. So we're going to have log, and we're going to have the x squared on top divided by 7 equals log of 112. Well, now that we have log on both sides and it's the same base, because remember this is log base 10, so we have log base 10 on each side, then we can actually drop those log base 10s. We're going to be left with just this x squared over 7 equals 112. And when we solve for x, we're going to multiply by 7 on both sides. So we're going to have x squared equals 784. And then we're going to take the square root. And remember, when we take the square root, you're doing plus minus. So x equals, and let's see what the square root of 784 is. Okay, 28. So x equals plus or minus 28. We're going to look back up to the original problem. The only x is right here. We cannot use a negative 28 here because I'll be trying to take log of a negative number. So x equals 28 is going to be our answer. For our next one, we're going to go through the same idea of combining to where we have one log statement on each side. So the left side is okay. So we have log of 5x plus 1 equals, and then on the right side, we can use our product rule. So because we have log of 2x plus 3 plus log of 2, using our product rule, we'll be able to combine those. We're going to have log of 2x plus 3 times 2. And again, the brackets are there just to let you know we're doing log of this entire thing. And then once we have the same log statement on each side, then we can get rid of those logs. So we're going to have 5x plus 1 equals 2x plus 3 times 2. We're going to distribute on the right side. So we'll have 5x plus 1 equals 4x plus 6. And then we're just going to solve for x. So we're going to subtract 4x from both sides. We're going to have x plus 1 equals 6. And subtract 1 from both sides. And we're going to get x equals 5. Now we need to double check. If we were to plug in 5, we would have 5 times 5, which is 25 plus 1 will be 26. So that is going to be greater than 0. And also here, whenever we have the 2 times 5, it's going to be 10 plus 3 will be 13. So again, that'll be positive. And to fully check, you would put this entire thing into your calculator. So you'd be doing the log of 26, determining that value, and then seeing if that's the same as log of 13 plus log of 2, which it will be. Okay, for C, this is going to be the same idea. So we're going to have log of 2x minus 1 equals log, and again, we're going to use our product rule, and I'm going to use brackets just to put those together. So x plus 3 times 3, and then once we have log base 10 on both sides, we can get rid of those logs. So we're going to have 2x minus 1, so 2x minus 1 equals that x plus 3 times 3, so 2x minus 1 equals, we distribute here, we're going to have 3x plus 9, and then we're just going to solve for x. And I'm going to choose to take the x's to the right side, so subtract 2x from both sides. So we have negative 1 equals 3x plus 9, and then subtract 9 from both sides. So we have negative 10 equals 3x, and then divide by that 3. So we're getting that x equals negative 10 thirds. But let's double check. If we were to plug that in, so negative 10 thirds times 2 is going to be negative 20 thirds, or negative 6 and change. And then negative 6 minus 1, that's going to give us a negative number. So we can't do log of a negative number. So we know it's not going to be negative 10 thirds. Since that was our only possible solution and it doesn't work, then we have no solution for this one. All right, let's look at D. Again, same idea, that we need to go through and use our product rule to get our log statements together, have one log statement. So we're going to have log of x times x plus 3 equals log of 10. And once we have the same base on both sides, we can drop those logs and have x times x plus 3 equals 10. So we have x squared plus 3x equals 10. We're going to move that 10 over. So subtract 10 from both sides. You're going to get x squared plus 3x minus 10 equals 0. And now we factor. We're going to factor so that we have x plus 5, x minus 2. And now we set each of these factors equal to 0. We're going to get that x is a negative 5 and x is a positive 2. We need to go back to the original equation and double check. So if we do log of negative 5, right away that is not going to work. Log of, let's see, if we do a 2, so log of 2, that's a positive. And log of 2 plus 3, that's going to be 5, which is also a positive. So that x equals 2 does work. Okay, let's talk about something everybody likes, and that is money. So the compound interest formula, A equals P onto 1 plus R over N to the NT, and we're going to use that to solve. There's a few things that we need to make a note of. So A is the accumulated value, or that's the same as the ending value. The P is your principal, and that's the same as your starting value. The R is your interest rate as a decimal. N is going to be the number of times the money is compounded per year. And T is going to be your time, and that's going to be in years. All right, so once you know what all these variables stand for, then really we're just plugging in numbers. So it's asking us, find how long it takes an investment of $5,000 to grow to $9,000 if it's invested at 14.7% compounded daily. Okay, so we have an ending or an accumulated amount of $9,000. Our principal, our initial amount, was $5,000, and that's going to be the initial amount you've invested, or if you're taking out a loan, the initial amount of the loan. And then we have 1 plus our rate of 14.7%. We're going to write as a decimal, so 0.147 over, and then compounded daily, there's going to be 365 days in a year, and that's going to be to the power of the n, so that's 365, times t. And it's asking us to solve for t. We want to find out how long. So we've got 9,000 equals this 5,000 onto 1 plus. Again, that rate was converted over to a decimal. So 0.147 divided by 365 to the power of 365t. The first thing we want to do is move this 5,000. Our goal is to have a base to a power by itself. And this 1 plus 0.147 over 365 is just a number. So it's the same, or its decimal equivalent, we can find out really quickly. So it's going to be the same as 1.000400274. And that's to the power of 365t. And again, we've got that 9,000 equals 5,000. So we're going to divide first. So the 5,000s go away, and we're going to simplify and reduce this 9,000 over 5,000 to be, it's the same as 9/5, which is 1.8 equals 1.000400274 to the power of 365t. And now we have a base to a power, and that power has our exponent. So if we take the natural log of both sides, we can use our power rule. And again, we're doing that so we can get this power in front. So we're going to have the natural log of 1.8 equals 365t times the natural log of 1.000400274. And we need to solve for t. So we're going to divide. And we're going to do two divisions at once, meaning we need to divide by that 365, and we need to divide by the natural log of 1.00040274. So we're going to divide both sides by that. So our answer is going to end up being that x equals the natural log of 1.8 over 365 times the natural log of 1.00040274. And we can get the decimal equivalent using our calculator. So the natural log of 1.8 divided by 365 times the natural log of 1.00040274. And that gives us 3.999. Or that's going to be that our time is about 4 years. And actually this x should be a t, because that's what we were solving for. All right, and one more word problem. So the formula a equals 37.3 e to the 0.0095 t power models the population of California, A, in millions, t years after the year 2000. So it's asking us first, what's the population of California in 2010? Well, 2010 is going to be 0 years after the year 2000. So to work out A, all we're going to do is plug in 0 for t. So we're going to have A, our final amount, equals 37.3. E to the 0.0095 times 0 power. Well, we can simplify that. That's going to be 37.3 times e, and this is going to be to the 0. E to the 0 is going to be 1. Because remember, any number besides 0 to the 0 power is the same as 1. So this is like 37.3 times 1, or A equals 37.3. So the answer, what was the population of California in 2010? It's not going to be 37.3, but it will be 37.3 million. Because it tells us that A is in millions. All right, let's look at B. When will the population of California reach 40 million? So basically, we're just going to plug in 40, or the ending number for the A, equals 37.3 times e to the 0.0095 t. Again, we want to get a base to the power by itself on one side, so we're going to first divide by 37.3. So we've got 40 over 37.3 equals e to 0.0095 t. Our next step is going to be to take the natural log of both sides. Because we have a base to a power, and we need to get that power down, taking the natural log of both sides is going to allow us to pull this power down. So we're going to have the natural log of 40 over 37.3 equals 0.0095 t times the natural log of e. Again, this natural log of e is the same as times 1, so we're not going to worry about it. I'm just going to erase it because it's the same thing as multiplying by 1. Then our next step, to get this t by itself, we need to move that 0.0095, and we're going to do that by division. So divide both sides by 0.0095. And we're going to end up with t equals the natural log of 40 over 37.3, and then all that divided by 0.0095. And we're going to get a decimal equivalent by putting in our calculator. So we have the natural log of 40 over 37.3, all divided by 0.0095, and that gives us 7.356. Now, it asks us what year or when will the population of California reach the 40 million. Remember that t is going to be the number of years after 2010. So this would be 2017.356, or sometime during 2017. Because again, we're going to take this number, that t, and we're adding 2010, which is our start point. And that's going to get us that somewhere in 2017.